Good morning, class. Today we are going to discuss about matrices and vector space. First, let's discuss about matrices. In this section, we are going to consider the collection of all m by n matrices with real value entries. And we denote this collection as capital M, and little n, where the little m stands for the number of rows and the little n stands for the number of columns. So for example, A is a table of 3 rows and 4 columns. So A is in. This notation means being an element in the collection. Or belong to. Right? So this matrix A is inside the collection M34, which means the collection of all 3 by 4 matrices, 3 rows, 4 columns, 12 entries. And each entry here is a real number, right? So you can see this is pi about 3.14 and this is E about 2.71828. All right, we use the notation little aij to denote the entry on the ith row and the jth column of the matrix A. So for example, for this matrix, little a23 stands for the entries on the second row and the third column. And so if you want to know what it is, you look for the second row and the third column. So right here, that's 1/2. Similarly, A32 means the entries of the matrix capital A on row 3, column 2. Row 3 is this one, and column 2 is this one, so the entry is pi. Another example, this matrix is inside or belongs to the collection of all 2 by 2 matrices. Right? Literally, the capital M here stands for the word matrix. And so if you look for the entries of B, for example, the entry on the first row, first column is obviously 1. The entry on the first row, second column is 2. The entry on the second row, first column, that's -3. And the entry on the second row, second column is 4. We can have matrices of only one column, like the matrix C, or matrix of only one row, like the matrix D. Now it turns out that Rn that we have been familiar with, for example R2, R3, is the collection of all matrices of n rows, one column. For example, the matrix C is of 4 rows, one column. So this is defined to be R4, the 4-dimensional vector space R4. So the first dimension can be thought of as the length, the second dimension can be thought of as the width, the third dimension can be thought of as the height, and the fourth dimension can be thought of as the time dimension. Now in special case, when you only have one row, one column, the matrix turns out to be the real number. Now when we consider bigger size matrices, for example, matrices of size 10 by 10, or in practice, matrices can well beyond the size 100 by 100. We need all the notations to write the matrices quickly. So we write capital A equals little aij inside the pair of square bracket. And then outside of that, we have a subindex little n by little n. This is an abbreviation for writing a mega matrix here. Right? Of course, this little m stands for the number of rows. This little n stands for the number of columns. And the little aij stands for a formula that is used to compute the entries on the ith row and the jth column. Let's consider an example. The matrix B is given by the formula here. Alright, so you can see that instead of writing a big matrix of 4 rows, 3 columns, we can just write as short as this one. And in case when we need, we can easily recover the matrix B as we wish. For example, if you want to compute the entry on the first row, first column is going to be Bij is equals to I minus j. So that means if you want to compute B11, it's going to be 1 minus 1, and that is going to be 0. Alright, so you get 0 here. Now, if you want to compute the next entry, the entries on the first row, second column, B12, then it's going to be I, which is 1, minus j, which is 2, and you are going to get negative 1. Alright, so we have computed this entry. The next entry on the first row, B13, is going to be 1 minus 3, row minus columns, according to the given formula. So this is going to be negative 2, exactly as shown here. So using the formula here, you can easily recover the other 9 entries, and you can do that at home on your own. Next, we are going to discuss about the operations on matrices. If you have 2 matrices of the same size, remember, they've got to be of the same size. Otherwise, you won't be able to perform the matrix addition. Adding 2 matrices is in fact just adding the corresponding entries on the same row and the same column. So for example, if you have the matrix A here and the matrix B, they are of the same size, 3 by 2, 3 by 2. So you can add them. Then you just add the first entry on the first row of A and B. So 1 plus 3, that's 4. Then you add the entries on the first row, second columns of A and B. So that's 3. And then you just do that entry-wise. And 1 with 1 is 2. Now, if A and B were of different sizes, for example, A here is of size 2 by 3, and B is of size 2 by 2, so different size, then you wouldn't be able to add A and B. Why? It's very simple. You can add 2 and 1, you can add 0 and 0, but you wouldn't be able to add 1 with something that you don't know here. Right. Another matrix operation is the scalar multiplication. It's actually just multiplying a real number to every entry of A. For example, if capital A is a matrix of size 3 by 3 with 9 entries here, then multiplying 3 to A, meaning that you are going to multiply number 3 with each entries of A. So 3 times 2 is 6, 3 times 3 is 9, 3 times 1 is 3, and you are going to do that entry-wise for every entry of A. Now, regarding the addition of matrices, there's a special matrix that when you add it with any other matrix, it will not change the matrix that you used to add with it. That's the zero matrix. So zero matrices are actually just matrices where all entries are zeros. Of course, if you add a zero matrix with any other matrix of the same size, you are going to get exactly the matrix that you used to add with the zero matrix. The next terminology is the negative. If you have a matrix A, then the negative of the matrix A is actually the matrix whose entries are the negative of the entries of the original matrix. For example, this matrix A is going to have its negative being this. And you can see that we flip the sign of every entries here. If we have matrix addition, then we also have the matrix subtraction. If A and B are two matrices of the same size, then A minus B is in fact being defined to be adding A with the negative of B. So we are going to add the entries of A with the negative entries of B. And that's just A, the entries of A minus the entries of B accordingly. For example, consider the two matrices A and B here. If you want to subtract A and B like this, then you will subtract 1 by 3 and you get negative 2. You will subtract 2 by 1 and you get 1. And you continue this fashion for all other entries of A and B. Subtract entry-wise. Alright, the collection of matrices of the same size together with the addition and the scalar multiplication that we have just mentioned above turns out to satisfy 10 special properties. The first property says that if you add two matrices of the same size, you end up getting another matrix that you denote as A plus B. And this summation matrix turns out to be of the same size as well. And we say that matrix addition is well defined. The second property is that the addition of two matrices turns out to be commutative. Matrix addition is also associative, which means you can perform the addition in any order that you wish. You add A and B first and then add with C. It's the same as adding B and C first, then add with A. If you add a matrix with a zero matrix, you will get the matrix A itself. If you add a matrix with its negative, you will end up getting the zero matrix. Property number 6 is that if you multiply a number, a scalar, to a matrix, you end up getting another matrix of the same size, just different entries. And we say that the scalar multiplication is well defined. The scalar multiplication is associative, which means instead of multiplying the scalar s to A first and then multiply the scalar r to the result, you can just first perform the real number multiplication between the two real numbers r and s, and then scalarly multiply the result to the matrix A. The eighth property can be considered as the left distribution of scalar multiplication. If you multiply a scalar to the summation of two matrices, then it's like you multiply the scalar with each matrix and then add the results together. The ninth property is considered as the right distribution of scalar multiplication. By the right distribution, we literally mean that we are going to distribute the matrix A to the sum of two real numbers r and s from the right of the sum. Right? 9 and 8 are different because in 8 we distribute a number into the sum of two matrices, while in 9 we distribute a matrix into the sum of two real numbers. The 10th property says that if you multiply the number 1 with a matrix A, then you are going to get exactly the matrix A, which is obvious. Now we are going to prove these 10 properties. The first property is kind of obvious. The sixth property is also obvious, right? The 10th property is obvious. The fourth is also obvious to see. The fifth property is also very obvious, but we are going to need to write something. So in class today, we are going to prove property number 2 and number 3. And then say property number 8 as well. And I'm going to leave the rest for you to try at home. So let's prove the second property. So you want to prove, we need to show that A plus B is the same as B plus A. Alright, so most of you probably have never been working with proof. So here's how we are going to start. So you want to prove that A plus B equals B plus A. In order to prove an equality, we either start from the left and try to transform it so that it looks exactly like the right hand side. Or you can start from the right hand side and try to transform it so that it looks exactly like the left hand side. Or we can start from both the left and the right, transform both of them at the same time, try to make them similar to something in the middle. That's also a good strategy. So in this case, I'm going to start from the left and I'm going to show that eventually it is going to look exactly like the right hand side. Now if you start adding two matrices A and B, you know that you will have to add them entry-wise. So that means you will have to start with a matrix A of size m by n. So if you want to write it down explicitly, then you are going to do this. And then you write down the matrix B explicitly. Remember to keep the number of rows and the number of columns being general, because you wouldn't know what exactly m and n are. And you shouldn't start with any specific m and specific n, because if you do so, then it would mean that you have just proven the property for the collections of all matrices of that size of m and n that you chose. Right? Here we want to prove that this is true for any m and any n, so we need to keep m and n being general, the most general we can. Alright, and you see that if you add two matrices of the size m by n, then we end up having another matrix of the size m by n, where each entry is going to be just the summation of the two corresponding entries of A and B. For the entries on the first row, first column of the summation matrix, we are going to get A11 plus B11. For the entries on the first row, second column, we are going to have A12 plus B12. And if you continue this fashion, you are going to get A1n plus B1n. Of course, it's going to be just tedious work to write the orders. Now, when we write A plus B, this addition notation means the matrix addition. It is going to be different from the addition that we write here, because this is the addition of the two real numbers. So the addition that we wrote here are the familiar additions that we have been playing with for many years, right? But for this addition, it's the matrix addition. It's not the addition of real numbers. That is why we need to check if it still satisfies the commutative property or not. So, with that being said, A11 plus B11 is the same as B11 plus A11. And then B12 plus A12. All right. And it's just tedious work to write out all orders. Now, if you look at this, it turns out that this is the result of adding the matrix B with the matrix A. And so the matrix addition is really commutative, and that commutative property comes from the fact that the addition of real numbers are commutative. So now you have seen that proving the properties of matrices is not hard. We actually just utilize what we know from the operations that we have been familiar with when we work with real numbers. However, the writing work is really heavy and tedious. And in order to reduce the writing work that we have done here, we can utilize the notation that we have learned from the first slide. Instead of having to write A and B explicitly, I can do A plus B with the notation Aij m by n plus Bij m by n. And because we know that adding two matrices turn out to be adding entries wise, that means if you know a formula for the entries of A, and if we have a formula for the entries of B, then we just add the two formulas of A and B. Of course, they are at the same position, Ij, so we wouldn't have to worry about that. So it's like we are going to get another matrix of the same size m by n, and the entries are going to be computed by adding Aij and Bij. Again, this is the addition of matrices. Right? So this is also the addition of matrices. However, inside the square bracket is the addition of real numbers. And the addition of two real numbers is commutative. So you are going to get Bij plus Aij m by n. Now this turns out to be adding Bij m by n with Aij m by n. And when you write the addition here, we really mean the addition of two matrices. The first matrix is the capital B matrix, and the second one is the capital A matrix. And so we have successfully proven that A plus B is equals to B plus A. And we are done. All right, let's prove property number 3 utilizing the abbreviation notation here. So we need to show that A plus B then plus C is the same as A plus B plus C. We are going to start with the left hand side. So we use the notation Aij in the square brackets m by n. And really, when the size is not really important, we can ignore them as well. So this notation means that we are looking at the matrix A of size m by n, and because the sizes are not important, so I'm going to drop them here to shorten our notation. But really, this is not just one entry. It can be a large table of more than 100 entries. And then I'm going to write C entry-wise using the abbreviation. All right, so adding two matrices is the same as adding the entries correspondingly. So this means that the result is going to be another matrix. That's why we use the pair of brackets here. And this new matrix is the summation matrix computed by adding the entries of A and the entries of B correspondingly. Now, this result matrix will be added with the matrix C. And so you are going to add the entries Aij plus Bij. This is the entry on the ith row and the jth column of the summation matrix. And it is going to be added with the entries on the ith row and the jth column of the C matrix. I'm going to use a different color for the addition of matrices. On this row, this is the addition of real numbers. But this is the addition of matrices, so that's a red plus. Now we are adding three real numbers, and the addition of real numbers is associative. So we can, in fact, add Bij and Cij first, then add with Aij later. Then we have the pair of brackets here to denote that we are working with matrices. This turns out to be adding the matrix whose entries are computed by the Aij formula. Matrix addition with the second matrix being the matrix whose entries is computed by the formula Bij plus Cij. Then you can further break down this one to be Bij in the bracket, which means the matrix B, plus Cij in the bracket, which means the matrix C. And so we have successfully proven that A plus B then plus C is the same as adding B and C first, then plus A. We need to show that a scalar multiplication of a real number R with the summation of two matrices A and B is the same as multiplying scalarly R with A, R with B, and then add the result together. Now let's start from the left. So again, I'm going to utilize the abbreviation. Right? I should have written m by n and b ij m by n. But because when we add the matrices, it's implicitly understood that we are adding matrices of the same size, same number of rows, and same number of columns. So it would not be necessary to keep the m by n because it's just lengthened our notation. Now you cannot distribute the R right away because the addition here is the matrix addition. And we have not yet known whether the scalar multiply is going to distribute into the addition of matrices. That's what we are trying to prove, right? So we cannot distribute the R right now. But after we prove everything here, then yes, we can do that. But right now we haven't known whether it is true or not. We cannot use it. All right. One very common mistake when writing proof is that you use what you are trying to prove, or you use what has not yet been proved. If we cannot distribute R, how can we perform? Well, if we cannot do the scalar multiplication here right away, we can perform from inside first because that's just the addition of two matrices and we know how to add matrices. So as said, we are going to add the two matrices A and B first, and that's just adding the two real numbers Aij and Bij. All right. Here the addition again is the addition of two real numbers, and this addition is far different from the red addition here. All right, so this means that we are going to scalarly multiply the number R with the matrix whose entries are computed by the formula Aij plus Bij. And now we can multiply R into each of the entries of this matrix. That's just scalar multiplication with matrix. So then inside the matrix here, at every entry, right, at each entry, we have a multiplication and an addition here. Now, what's the difference between this and this? Right. This means the scalar multiplication of the number R with the matrix. But this means we are going to multiply the number R, the real number R, with the sum of two real numbers. And we know if we multiply a number to the sum of two numbers, we can distribute it, right? So we are going to have R times Aij plus R times Bij. So now this is what happening inside a matrix at every entry. And then you can perform further. We are going to split them into two. Now this is the summation of matrices, right? It's different from the additions above it. Next, I am going to write this one as R times capital A. Alright, if you multiply a number to a matrix, you are going to multiply a number with each of the entry of the matrix. This is like R times the matrix B scalarly, and this is the matrix addition, and we have successfully proven the eighth property. Alright, so let's see, we have proven this, this, and this. So there are still property 5, 7, and 9 for you to try at home. Alright. Writing proof is hard, and so these are kind of easy examples for you to try to practice before you actually write something more complicated. Now, surprisingly, not only matrices of the same size would satisfy the 10 properties. There are many, many more other set of elements with well-defined addition and scalar multiplication, which also satisfy the same similar 10 properties here. And each of these is called the vector space. So let's discuss about vector space. Well, a vector space is actually just a set or a collection of elements that, together with the addition and the scalar multiplication, satisfy the 10 properties that are similar to the 10 properties that we have seen. So first, the addition is well defined. That means if you have an A and a B in the set V, after adding the two, you are going to get something new denoted as A plus B, and that is being in V as well. Right. If you start with an A in V, a B in V, and after you add them, you end up being outside of V, that is not going to be a well-defined addition. The second property is commutative. You also have associativity. The existence of the zero elements, that is the elements that act just like the zero number or act just like the zero matrix. However, because we are working with the V, the set V of some sort of elements that can be real numbers, can be matrices, or can be otherwise. So we are going to write 0 V to remind ourselves that this is the 0 in the set V, not the matrix 0, not the zero number. All right. The fifth property is about the negative elements. Right. If a set V wants to be a vector space, then every element inside V has got to have a negative element. That is an element when you add with A, you are going to have the zero element of A. So you can see that these are very similar to the properties of real numbers. But when you define or when you consider a new set of elements, you got to be very careful because you are working in a new environment, an environment that is not familiar. So we need to check everything carefully before we can use. Additionally, you also have the 5 properties for the scalar multiplication. Whatever the scalar multiplication you would want to define on V, it's got to be first being well defined, which means you multiply a number with an element in V. The A here is not a matrix. It can be a matrix, it can be a number, it can be anything depending on what type of set V you are considering. But whatever, if you multiply the scalar R with the element A in V, the result is going to be another element in V. The 7th property is the associativity property, right? And 8 and 9 are the left and the right distributive property. The 10th property is kind of similar to what we have seen from matrices. The collection of all matrices of the same size is in fact a vector space together with the addition and the scalar multiplication entry-wise. Rn is also a vector space, right? Because Rn is actually just special matrices, the matrices of only one column. Now, let's consider something other than what we have known so far. F of S is the notation for the collection of all real value functions defined on a subset of the real number. For example, the S can be an open interval, a closed interval, or sometimes even the whole set of real numbers. On this collection of real value functions, we define the pointwise addition. If you add two functions, f and g, you will end up getting a new function that is denoted as f plus g. This is a new function. We call it the summation function and denote it as f plus g. Right? So this whole thing can just be rewritten as an h function if you want. So you may have the function f just like a number machine here. If you input an x value, the output is going to give you f of x. You also have a number machine g. When you enter an x, you are going to get the output g of x. Then the function f plus g is a new function. If you enter an input x, at the output, you are going to get f of x plus g of x. This guy is how we compute f plus g when the input is x. How we compute f plus g when the input is x. Similarly, pointwise scalar multiplication. Right? If you have a function f that takes in an input x and spit out an output f of x, then r of f is a new function, so that when you enter an input x, the new function is going to spit out a value that is computed by r times f of x, which is this one. All right? And because this is the result of the function rf, we also write it as rf of x. And that's exactly what we write here. Right? All right, for example, if you consider f being this function and g being the square function here, then we are going to have f plus g being the summation function. And this function is computed by the formula f plus g of x being f of x plus g of x. And so you can combine the like terms and you get this function. So the summation function turns out to be this. Similarly, if you want to compute 4f of x, then you multiply 4 with the function f, and you get 4x cubed plus 12x squared. This collection of all real value functions, together with the pointwise addition and the pointwise scalar multiplication, turns out to be a vector space. That means we need to check all 10 properties. First of all, we need to check whether f plus g is well defined. Well, the fact is that if we add two functions of the same domain S, which means any x in S, you can compute f of x, you can compute g of x, so of course you can compute f of x plus g of x. So this new function, f plus g, is going to work with any x in the set S. In other words, the new function has the same domain as f and g are. So the addition here is a well-defined addition. Similarly, you can argue the same thing for the scalar multiplication being well-defined. Next, I'm going to discuss the proof of the other properties. We'll have to double check if f plus g equals g plus f, commutative property, associative property, the existence of the zero element in the set of real value functions. So this is going to be called the zero function, right? The existence of the negative elements of any element f in the collection of real value functions. Then the associativity for the scalar multiplication, the left and the right distributive properties for the scalar multiplication, and multiplying with the number 1. Well, the 10 properties is kind of obvious as well, right? So let's discuss about property number 3 and property number 7 here. Now, is the additions of functions associative? Right? In order to prove that two functions are equal to each other, we need to check whether or not they are going to produce the same output when we enter the same input. Right? So we are going to enter the input for the left function, enter the input for the right function, and see whether the output are the same. Now let's start with the left-hand side. When we enter the input x to the left function, right, we write x, we do not enter any specific real number x, because that just means we have just checked the property for that specific value. We want to keep everything as most general as we can. So we write x instead of 1, 2, 3, or any other real numbers. Back to what we want to prove. We want to prove that entering x as the input for the left function is the same as what we are going to get with the right function. All right, by the definition. So this is by the definition of the additions of functions. The addition of functions here, if we want to add two functions, f plus g and the function h, then we are going to add them entry-wise. So this addition is far different from this addition. This is the addition of a real number and another real number. Now next we further break down this one So this is the addition of two functions f and g. And in order to add them, we are going to add them entry-wise. So again, this is the definition again. All right. In which we break down f of x and g of x. Now, from here, we have this addition and this addition. They are the additions of real numbers f of x, g of x, and h of x. Real numbers. This is also a real number. And this is also a real number. All right. And we know that the additions of real numbers is associative. So we can add g of x and h of x first before adding with f of x. Now this one turns out to be, by definition. And then we are going to combine this and this. We are going to get f plus g plus h. And this is also by the definitions of the summation of two functions, f and g plus h. F and g plus h. So now we need to be very, very conscious of which addition is the addition of functions and which additions is the addition of real numbers. So I'm going to use the red color for the addition of functions, right? The addition of two functions g and h. But this is the addition of two real numbers f of x and g plus h of x. However, when we move to the last row, this is the addition between two functions, and this is also the addition between two functions. Back here, this is also the addition of functions. Right? This is also the addition of function here, but this is the addition of real numbers. So be clear that although you may use the same notation, but you should always be conscious of what the notation means. Similarly, we can check the property number 7, the associativity for the scalar multiplication. All right, so we want to check if the function on the left is equals to the function on the right. If we want to do so, it's the same as we want to show that when we enter the input x to the function on the left and entering the input x to the function on the right, we are going to get the same answer, the same output. So start from the left. All right. We have a function with the input x. This function is created by scalarly multiplying the real number r with a function sf. So by the definition of scalar multiplication, right, we are going to multiply r with the output sf of x. Now look at the inside part here. This means that we are computing the output of the function sf when the input is x. What does that mean by sf? Sf means you scalarly multiply the real number s with the function f. So by definition of scalar multiplication, we are going to multiply the number s with the output f of x. All right. Now, at this point, we already have a number r, a number s, and the number f of x. They are real numbers and being multiplied together. If you multiply three real numbers together, you can combine the r and the s first. Then multiply this real number with the real number f of x. but multiply the real number Rs with the real number f of x, or with the output f of x, is the same as computing the output of the function Rs times f scalarly when the input is x. All right. We have checked the third property and the seventh property. So your job at home is to try to check the second, the fourth, the fifth, the eighth, and the ninth property on your own. Right? If you have questions, bring it to class to discuss.